Welcome back, everybody. Hope everyone's first 2 days were good. I realized way too late that I forgot to take attendance yesterday, so everyone was here yesterday, right? We're all good with that. We're all here. This time, I'm better. I'm more prepared. I've got scratch paper, so please sign in when you get it when it comes to you. You don't need to put anything other than really your name. If your name is going to show up differently on Canvas, please let me know. So please put the name that's going to be on Canvas. But anyways, so last time we left off with doing integral substitution. And the other thing I had forgotten to mention, I had mentioned it, but I hadn't shown it. Well, we're not doing a crossword right now. Um, uh, So if you just search Paul's online calculus two notes, calc two notes, this place will pop up. This is a great resource for practice problems and stuff. And yes, the organization of his material may be a little bit flipped from mine, his or hers, or theirs. I don't know this person offhand, but all of their stuff is kind of in the same order. That's kind of, I mean, most calc courses are organized in somewhat the same order. So today we're going to be going over the integration by parts. And then up at the top, you see practice problems. The assignment problems are like, so the great thing about the practice problems is that they all have solutions. So you can click it and expand it, and you can one thing I love about this especially, and this is the way you should do it if you're stumped, is start the solution. Because then he gives you ideas on how he or she or they, Paul, I guess their name is, gives you where to start. And then you can keep showing more and more steps, but the goal is to be an active participant in the process. So if you can get started, then try and finish the rest of it and then check your work. The assignment problems are ones that Paul gives to his own, his or hers or their own student. So these ones do not have answers, but you can always use things like Wolfram Alpha and stuff to verify that it's correct. So very, very great resource to use. It has notes for all of it too. So I would really, really recommend it. But anyways, back to our stuff. We were still going over integral substitution. This time I'm doing it with definite integrals. So what should we choose for you here? Sine is a great choice. Now, I'm going to do this. Remember, there are two different ways to do definite integrals with integral substitution. You can either keep the bounds the same and label them in terms of the original variable, or you can change the bounds with the u substitution. So option one is the is what I'm going to do for this one. Option one is to I forget which from my class originally for calc if I do changing bounds is the first option. I think I do, but let's do it this way because I want to do B for a specific reason. So keep the bounds keep bounds in terms of theta. So you can keep your bounds in terms of your original variable, should you like. So if you do so, you're going to make u equal to sine of theta. So that means that du is equal to cosine theta d theta. And this is basically one of the only times where I don't really want to buy. I mean, I'm gonna still do it because that's the way I've always done integral substitutions. I'm gonna solve for d theta, but you might notice right off the bat that there's a cosine, cosine, and a d theta and a d theta. So you can just immediately replace cosine d theta with du. That being said, I just like to be able to do it for more general terms. This is a really nifty situation where it automatically pairs up. So that's something I typically avoid, but if you feel comfortable doing that way, more power to you. So that means that d theta is equal to 1 over cosine theta du. So the integral now becomes uh, from theta equals negative pi over 4 to theta equals pi over 2 of cosine of theta e to the u times 1 over cosine theta du. And the cosine thetas cancel. And a couple things about this. This is the way you should write it if you're not going to change the bounds. If you're not going to change the bounds, you need to keep them writing them as thetas. You should write theta equals. Or something to remind yourself that it is in terms of theta. Technically speaking, it should be there regardless. But I know some of these problems can end up taking a long time sometimes. But there needs to be something to distinguish this. And I'm doing this because I want to help you. When we start talking about trigonometric substitution, you want to make sure that you're sticking with like you're being consistent. So I really not recommend, require that the theta be there if you're not going to change the bounds. So this now becomes the integral from theta equals negative pi over 4. Sorry, the app is going lame, and so I need to reload it. It starts to lag after a little while. Theta equals negative pi over 4 to theta equals pi over 2. In fact, you know what? We're big boys now. We can even skip that step and just immediately realize that because the cosines have canceled, now we just have an integral of e to the u, and the antiderivative of e to the u is itself. So this is equal to e to the u evaluated from theta equals negative pi over 4 to theta equals pi over 2. I'm still writing the thetas because the integral, the result is still in terms of u. These are not u bounds, these are theta bounds. Now what I'm going to do is switch it back to being in terms of theta. So this is e to the sine theta from negative pi over 4 to pi over 2. Now that I've gotten it back in terms of theta, I can drop the theta equals because these are theta bounds. And doing so, I get e to the sine of pi over 2, which is 1. There we go. So it's e to the first power, or just e, minus sine of negative pi over 4. That's going to be in the fourth quadrant. Is sine positive or negative there? Negative. Good job. Good job. We all know where it is. Yes, sine is negative in the fourth quadrant, and sine of it, and the reference angle being pi over 4, that'd be square root 2 over 2. So it's e to the negative square root 2 over 2. And that is our answer. And if you use your calculator, you can verify this. You can check your work. Plug this in your calculator, e minus e. And when you plug it into your calculator, you're going to have to do e to the first power for whatever reason. You can't just put e minus e to the negative square root 2 over 2. And if you plug that in, it should give you a decimal answer. Then compute the definite integral. It should be the same number. And if it's not, you may have made an error somewhere. Most likely an algebra error. So, any questions on that? Option 2 is to change the bounds. So we've got the integral from -1 to 2 of 12w minus 10 times like that quantity times e to the 3w squared minus 5w dw. And so a good choice for you is anything inside of a function. So in this case, inside of the e. So we will make u equal to 3w squared minus 5w, which means that du is equal to, parentheses, 6w minus 5 dw, meaning that dw is equal to 1 over 6w minus 5 du. Now we're going to change the bounds. And the important thing to understand and remind yourself of is the bottom bound still stays the bottom bound, even if it becomes larger. Bottom bound stays the bottom bound, upper bound still stays the upper bound. So when W is equal to 2, U will equal 3 times 2 squared minus 5 times 2, which is 3 times 4, 12 minus 10, 2. And when W is equal to -1, we get that U is equal to 3W, 3 times 1 squared, the 3 minus 5, sorry, minus -5, so plus 5, so that would be 8. So typically speaking, by the way, this step I do in my head or I just write the number. If I'm doing this on an exam, I don't write the U equals 3 times 2 squared minus 5 times 2. I just write the 2. Or I do it in my head or on my calculator because I don't need to see that work, but I'm just doing it for our note-taking purposes. So when U is equal, when W is equal to -1, we get 3 minus -5 is 8. So the W equals 2 is the top bound. The W equals -1 was the bottom bound. So this now becomes the integral from 8 to 2 of 12W minus 10 e to the u times 1 over 6W minus 5 du. Any questions so far? Both have their merits, by the way. This option and the other option both have their merits. We'll talk about the pros and cons of each as we go along. And at current standpoint, it doesn't look exactly right, but the fact of the matter is that 12W minus 10 has a common factor of 2. This is equal to 2 times 6W minus 5, meaning that the 6W minus 5s cancel. And then to save on time, since that's all gone, we have 2e to the u. That's all that's left, right? Left, right. Correct. That's all we have left. So the integral of 2e to the u is 2e to the u. And thusly, this is the integral, or this is now, we found the antiderivative, it's 2e to the u, evaluated from 8 to 2, which is 2e squared minus 2e to the 8th. And that is our answer. Yes, it's negative, but this is a definite integral with no context to it. So it can be negative. If we're talking about area, then it's a different question. So any questions on this one? So just putting them both up on the screen, the only difference is when exactly you need to plug in the numbers and change the bounds. In this one, you have to wait until the end to get it back. Like in this one, you're changing the bounds basically at the end. Here, you're changing the bounds at the beginning. Your choice. It doesn't really matter. Sometimes one is better than the other. Sometimes, but they both work regardless. It's kind of like with elimination and substitution with 2x2 systems of equations, right? Elimination is just as good as substitution, but there are some circumstances where substitution's better. Same idea.
Is it like a use by use?
It's a case by case basis. I usually like changing the bounds personally, but that because then I don't have to write theta equals theta equals theta equals, and which we will see with the integrals that we will start dealing with. They might take a little longer. So keep consistently writing theta equals can take up some time. So that's why I like changing the bounds. But it's all your choice. This last one. If you took my class, you might have learned that there was a fast way to do this one. But until we get to the next page, which we'll talk about in a second, the only way to do it is with an integral substitution. We'll make u equal to 5x plus 2 so that du is equal to 5 dx. So that means the dx is equal to 1/5 du. And if we're changing the bounds, So this time from now on in this class, I'm not going to show the work of changing the bounds. I'm not going to be showing what I did right here. I'm not going to be showing that. I'm just going to do what I did on the second one, where I write what the new bound will be. And you can even skip that and just change the bounds on the integral. That is okay too. So if you like, so what I'm saying is if you want to write this to be from 2 to 12 for your new integral, you're allowed to do that. But I'll show you what I did. So W equals 2 implies that U is equal to 5 times 2 plus 2. That's 12. Oh, that's a typo. That's a typo. Thank you. Good catch. X equals 2, that means U is equal to 12, and X equals 0. That gives us 5 times 0 plus 2, which means that U is equal to 2. So once again, you can do this in your head. This is just for our note-taking purposes. You can change the bounds without doing that written down. This becomes 1 over U times 1/5 du, which is going to be 1/5 natural log of the absolute value of U evaluated from 2 to 12. And since I've changed the bounds, I don't need to write U equals or whatever, and I don't need to worry about it. I can just immediately plug it in, and it becomes 1/5 natural log of 12 minus 1/5 natural log of 2. The absolute value signs are redundant. They're unnecessary, so we can drop them. And then if you want to be cheeky, or what, or if you're a badass with your knowledge of logarithms, natural log of 6 raised to the 1/5 power. I'm okay with either. But if you do write natural log of 6 to the 1/5 on your exam, you will get like you will hear a visible ooh from me, like, ooh, nice. That's real cool. Did a good job. Remember your logarithms. So I'll just put lols right there. Cool? Any questions? Okie dokie. So these ones, I need you to know that you can do these ones, and you can do them quickly. So if you ever have a linear term inside of a function that we know the integral of, so we know the antiderivative of sine, we know the antiderivative of cosine, we know the antiderivative of e, we know the antiderivative of 1 over x. So if you have those and you replace the x with a linear term, ax plus b, you can do these integrals very quick. The antiderivative, the indefinite integral of sine of ax plus b dx is equal to 1 over a, negative 1 over a cosine of ax plus b, plus a constant c. And the reason for that, if you don't see it right off the bat, is you make a u substitution. You make u equal to ax plus b. Then du will equal a dx. So that's where you get that 1 over a coming from. That's where the 1 over a shows up. So the antiderivative of sine of ax plus b is equal to 1 over negative 1 over a cosine of ax plus b, because the antiderivative of sine is negative cosine. Similarly, cosines would be 1 over a sine of ax plus b. E's would be 1 over a e to the ax plus b. Oh, but I'm forgetting my consistency. And then the last one would be 1 over a ln of the absolute value of ax plus b plus constant c. And these can even be generalized even more. If you have the antiderivative of sine squared, well, I mean, we can even write this one off on the side. Other examples. The antiderivative or the indefinite integral of secant squared of ax plus b dx is going to equal 1 over a tangent of ax plus b plus a constant c. Same idea, because the antiderivative of secant squared is tangent, because the derivative of tangent is secant squared, and so on and so forth. We can do this for a lot of different functions that we know of. But what I will tell you, especially when we get to 1.4, when we talk about partial fraction decomposition, this guy will show up a lot. The 1 over ax plus b. So yes, you can do an integral substitution. It's fine. It works, but it takes time that you could be spent doing other things. So if you can have these ones kind of on lockdown, that's great. Much like with anything in mathematics, the more you practice it, the faster you get at it. Just like when you were doing trig identities and knowing your trig values and stuff, as you got better, faster, like as you did it more, you got faster at it. Same thing will happen here. But out of all of them, this is probably the most important, the most commonly used for this class. So, as an example, if you've got the integral of 8 e to the 8x dw, 8x dx, apologies, that'll just be 1/8 e to the 8x plus a constant c. Immediate. No need to do an integral substitution. It's unnecessary. It's a waste of your time. And now, like sigma Chad, right? That's what your kids say. That's a uppercase sigma, by the way, in case you did not remember. Then you could do this one very quick. This immediately becomes 1/5 natural log of the absolute value of 5x plus 2, evaluated from 0 to 2. Yes, the bounds are different. It's because it's back in terms of just x. I didn't need to change the bounds because I already knew what the antiderivative would be in terms of x right from the get-go. And so this will become 1/5 natural log of 12 minus natural log, or 1/5 natural log of 2, just like before. But now we did it way faster. Surefire way to impress your significant other. If you can do that, that's it's pretty important. Okay? Any questions? All right. Now, we don't talk about this one too often in Calc 1, but it will play a role here. If the degree of your numerator is larger than the degree of your denominator, you can perform long division, because as it stands, that integral is not really feasible. I mean, there is a way to do it with the last option, the reverse engineered U substitution, which you'll know what that means if you took my class, but if for Calc 1, but this is what I call it. You'll see in a second. You can use reverse engineered U substitution, but that's only because it's y squared. If that was like y to the 15th, it would not be nearly as feasible. So sometimes you have to do long division. We can do synthetic on this one, luckily, because it's y minus 1, but that's not always, that's going to be very rare for us. So let's just go ahead and deal with the long division. So y minus 1 divided into y squared. And remember, you need placeholders for every power of y, including your constant. So it's plus 0y to the first power plus 0. Thought you were not going to have to deal with it anymore, didn't you? Thought you wouldn't have to deal with long division ever again. No, it's going to keep coming up again and again and again. And then when you become in grad school, they show you how to do polynomial division with multivariable, and that's no fun. That's awful. Don't do it. Burn your corneas. So anyways, how many times does y go into y squared? Well, it goes into it y times. You got y squared minus y. Subtract. We got y plus 0. I mean, you don't even really need to write the 0. And it goes into it one time. Y minus 1. Subtract. And we get 1. Positive 1, because it's minus a negative 1. So, by the division algorithm, This says that this is equal to your quotient, which is y plus 1 plus your remainder divided by your divisor. So remember, so long division, p of x divided by d of x is equal to q of x plus r of x divided by d of x. That's what the division algorithm says, is that if you take two polynomials and you divide p of x, which we call our dividend, and divide it by our divisor, you get a quotient plus the remainder divided by your divisor. That's what the division algorithm states. So this is our quotient. This is our remainder. That's why we've converted into a quotient plus our remainder divided by our divisor. And now it's a lot more approachable. The antiderivative of y is 1/2 y squared. The antiderivative of 1 is y. And then, yes, we could do an integral substitution. We can make u equal to y minus 1 and take care of it, and it'd be fine. But that's unnecessary. We already learned if you have a linear term like that, you could just write this. So it's going to be 1 over 1, which is just 1. So plus natural log of the absolute value of y minus 1 plus a constant c. Any questions on that? It's okay if there are. Okay. Then trig identities, they're going to come back again and again and again. Trig identities, specifically your knowledge of the Pythagorean identities. Remember, sine squared plus cosine squared equals 1, and then all the other ones, right? So what we're going to do is we're going to multiply this by, because right now, you could try and make u equal to cosine of alpha. That will not really help very much. It won't really help very much. It'll help a little bit, but not a lot. You'll have to do, like, if you do that, you'll have to do a little bit of trickery to get it into the right format. A nicer way to do it is to multiply by the conjugate, 1 minus sine alpha divided by 1 minus sine alpha, cleverly multiplying by 1. And what that will give us is the integral of 1 minus sine squared alpha divided by cosine of alpha times 1 minus sine alpha d alpha. And 1 minus sine squared alpha is cosine squared. Yes. There we go. Cosine squared alpha. So one of the cosines cancels. We have the integral of cosine of alpha divided by 1 minus sine alpha d alpha. I like using as many different types of variables as possible because the variable doesn't really matter. And from here, it's going to be a nice integral substitution. You should make u equal to 1 minus sine alpha. Yes. Then du is equal to negative cosine of alpha d alpha. So d alpha is equal to negative 1 over cosine of alpha du. So this will become, I mean, and this is one where you could just kind of replace the cosine alpha d alpha with just a negative 1 because of how, or just a negative du because of how it works. But let's do it the old-fashioned way. Cosine of alpha over u times negative 1 over cosine of alpha du. Cosine alphas cancel. We've got the integral of -1 over u. That'll be negative natural log of the absolute value of u. U plus a constant c. And therefore, it's natural log, a negative natural log of the absolute value of 1 minus sine of alpha plus a constant c. Any questions on that? I think actually, technically speaking, the absolute value signs are that right there are redundant. They're unnecessary because sine alpha is always between -1 and 1. Can never exceed 1. So the inside is always going to be greater than or equal to 0. So I guess we could replace those and be more technically correct. Put that SH in the actually, that strong SH. Actually, it's not necessary to have those. And that's how you make friends. True story. All right. Any questions on that one? Last one is what I like to coin as reverse engineered U substitution. And this typically happens when the inside of something has a smaller or equal power to the outside. So x squared on the outside, x to the first power, smaller power on the inside. And it would also work if you did x squared and then an x squared minus 1 on the inside. That would also be a good candidate for this. And this might seem contrived. This might seem like such a weird thing, but we will actually utilize this in trigonometric substitution, unit 1.3. I mean, ish. So, much like before with integral substitutions, a good choice of u is the inside of a function. So in this case, inside of the square root, you get that u is equal to x minus 1, so that du is just equal to dx. And so don't write this down. In fact, I'm going to do something fun. So you'd get that this is the integral of x squared times the square root of u du. And that doesn't look much better. However, because we have u equal to x minus 1, we can write x in terms of u. So what we're going to do is we're going to make this show us that x is equal to u plus 1. So this equals the integral of u plus 1 squared times the square root of u du. And that is more feasible to approach because in its current standpoint, yeah, it's a little hard to get it to be done. However, since this is just a u plus 1 squared, we could FOIL that out. We're big boys and girls. We could do that. This is going to be the integral of u squared plus 2u plus 1 times u to the 1/2 du. And we've got to distribute that u to the 1/2. U to the second power times u to the 1/2, that's u to the 5/2. Plus 2u to the 3/2 plus u to the 1/2 du. At which point we can integrate and do the power rule a bunch. Got u to the 7/2 over 7/2 plus 2u to the 5/2 over 5/2 plus u to the 3/2 over 3/2 plus a constant c. And just to make sure you guys get carpal tunnel quicker, we just have to rewrite this again in terms of x now because our original integral was in terms of x. And we get our final answer, which is 2/7 x minus 1 to the 7/2 plus 4/5 x minus 1 to the 5/2 plus 2/3 x minus 1 to the 3/2 plus a constant c. All right. And now we need a granola bar. It's a lot of writing. Any questions on any of those techniques? Anything like that? We're all good? Johnson & Johnson, no tears? For the most part, maybe a little bit of soap in the eye, a little bit of crying. Okay, good. Good. So that will complete the crash course. Once again, the first quiz on Tuesday will be completely on Calc 1 material with a heavier emphasis on integral substitution. So that's why we spent far more time on this than the derivatives and the limits. Okay, now we get into actual Calc 2 material. So integration by parts, which just to make it quick to write, if we ever have to say it out loud, this is IBP. Integration by parts. So what we learned in Calc 1 was integral substitution, which is essentially integration's version of the chain rule. And as a natural question that maybe you might ask is, well, we have a bunch of other rules. We have the quotient rule, we have the power rule, we have the other things. We have a power rule one, we have a power rule integration formula. And the question might be, do we have an analogous version of the product rule? And the answer is yes. That's what integration by parts actually represents. So let f and g be differentiable functions. Then we know by the product rule that the derivative of that product is equal to f prime g, wrong color, f prime of x, g of x, plus g prime of x, f of x, right? So because these two things are equal to each other, their integrals should be equal to each other. Sometimes you might see people do this. Don't write this down. And that's essentially what we're doing. We're going to make the, since both sides are equal to each other, we can put them inside of an integral and claim that those are equal. So that's what we're going to do. So we've got the integral of d dx of f of x, g of x, dx is equal to the integral of that sum. But remember, by the properties of integrals, you can break up a sum of an integral of a sum into a sum of integrals. So you can split it up into two pieces. So it's now f prime of x, g of x dx, plus the integral of g prime of x, f of x dx. Now, just to make it more readable, I'm going to write underneath these. I'm going to flip the order of these, and we'll see why in just a moment. Just trust me, bro. Right? Just trust me on this. For readability, we're going to rewrite this as g of x, f prime of x dx. And we're going to write this as f of x times g prime of x dx. Just trust. It's gonna help in just a moment for what integration by parts looks like. Now, what we know about derivatives and integrals is that they kind of are for the most part, they are inverse operations of each other. So if we have the integral of a derivative, that just undoes itself, right? And we just get back the integrand. So these things cancel essentially, and we've now got f of x, g of x is equal to, oh wait, no. I'm gonna write this since we don't have really enough space. So right here, I'm gonna subtract the integral of, which one do I want to do? Yes, subtract g of x f prime of x dx from both sides. And we're going to rearrange it a little bit. Oh, and let's write this underneath this. This is just equal to f of x times g of x. Okay. We're jumping around all over the place. Let's kind of recap one more time. The integral and the derivative, the derivative symbol basically cancel each other out. We've got f of x times g of x over here. And then what we're going to do is we're going to subtract off this piece from both sides. And then we're going to rearrange it. So what we've got is we've got the integral of f of x times g prime of x dx is equal to f of x times g of x minus the integral of g of x times f prime of x dx. Let's take a second. Let's digest it. And this is some grape nuts. Not even covered. We haven't even let that sit and melt for like 2 hours. You got to chew that for a while, right? We gotta take some time on that. You ever had grape nuts? Don't do it. It's bad. It's a cereal, right? Do we know what grape nuts are? Were we ever subjected to it as children? No, okay, you're lucky. So I'm basically putting this piece, let me, for the people watching the recording, I'm putting this piece over here. I'm basically flip-flopping the equation. And then I've subtracted, I've subtracted this from both sides. So it's f of x minus this function. That's where this is. And this is left by, and then let's fade it out. This is left by itself. That's what's happening. Any questions on that? Then, to make this more succinct, wait, are there any questions? Parker, did you have a question?
No.
Okay, just stretch. All right. To make it more succinct and to make it far nicer to look at, we'll use some integral substitutions. Namely, we'll make u equal to f of x and v equal to g of x to get that du is equal to f prime of x dx and dv is equal to g prime of x dx. And so we have this piece, and you might notice that that's right here. And then we also have this piece, which is right here. So u is f of x, dv is g prime of x dx, g is v, and f prime of x dx is dv. So we have the integration by parts formula. It is that the integral of u dv is equal to uv minus the integral of v du, which looks pretty intimidating, and it doesn't look like it's very helpful, but as you will see, it's actually very, very useful. The definite form is really no different. It's that the integral from a to b of u dv is equal to uv evaluated from a to b minus the integral from a to b of v du. That is integration by parts. That is the formula. Okay. That is a mouthful. Integral of u dv is equal to uv minus the integral of v du. So the reason why it's called integration by parts is because we have all the different parts. All the parts are kind of all around now. The u is over here, and it's also here. The dv is here, and that's the only place it shows up. And the whole goal is that you can utilize this to make things disintegrate, as you will see in just a moment. So that is the formula. Let's go ahead and look at an example, because as it stands with just integral substitution, there is no way to figure this out. The integral of x cosine x dx, there's not a way to do it. There will be a way later that doesn't require integration by parts, but that will require power series, which we haven't talked about until week 12. But until then, well, more specifically Taylor series, but I digress. So we can use integration by parts. So this is how it kind of gets set up. Now, some textbook, like it all depends on your textbook. Some people will make will make don't write this down. Some people will make it U and then DV, and then they'll write DU and then V here. Other textbooks will flip-flop these ones. They'll flip-flop these ones. They'll put V up top and then DV down at bottom because then it kind of lines up. U and V up top, DU and DV down at bottom. I like to do it this way, but a lot of textbooks like to do it the other way. They like to do it this way. So I'll show both on this example, or like on these two examples. Oh no, it's my class. It's my class. I do what I want. We're gonna do it my way. So you're gonna make U equal to X, and then that means that du is equal to dx by integral substitution, right? Like by if u is equal to x, then du is equal to dx. So the rest of it is therefore dv. So this is u, which means that this whole thing is dv. So dv is equal to cosine of x dx. One of my students, the way they memorized it, by the way, was they thought that it's equal to ultraviolet voodoo, VDU, voodoo, because it does feel a little bit like voodoo at first. It feels like magic. And so this is something we typically don't write, but this is what's going to happen with this dv. To find v, what we're trying to do is just find the antiderivative of cosine of x. But you can think of it by going like this. Integral of both sides. The integral of v, the integral of 1 dv is v. The integral of cosine x dx is sine of x. Yes, technically plus with a plus c, but we're going to just have a constant at the very, very end, so why bother putting it here when we're going to have to add a constant anyway? Any questions on that? I know it seems weird, but just suspend disbelief for just a moment. Any questions on how I got sine x or du?
We decided not to add the plus C because we'll add it later.
Yes, because we'll add it later. Like we could write it plus C1, and then once we actually find the antiderivative, we'd add another constant, but we can just combine those two constants into a global constant. So it's kind of like with the same situation when you have 1 plus 2x plus 3x squared dx. Yes, you could write x plus c sub 1 plus x squared plus c sub 2 plus x cubed plus c sub 3, but why write three different constants? You can just combine them as one constant. So that's the idea. Great question. So we've got integral of u dv by integration by parts. This is going to equal, I'm going to write this in purple, equals uv minus the integral of v du. I would recommend, as a little helpful tip, as a little pro tip, as it were, to hashtag get good at integration, write that every time. Write the integral, like write your u dv and then write uv minus the integral of v du. You'll memorize it faster. You will. And then also, this helps especially when you're starting out because now you have a blueprint for everything you need. This becomes the integral of, it becomes uv, so uv is x sine x minus the integral of v sine x du, which is dx. And that's something we can integrate, right? Sine of x dx, we know what that is. That's negative cosine. So this equals x sine x plus cosine of x plus a constant c. And boom, we've got it. Ta-da. Pretty cool. Pretty cool. We just saw that it is true. We saw why it works. We proved it to ourselves, why it works. But why is it useful? What is its purpose? What you're going to be trying to do is choosing a U that will make it go away or disintegrate or become easier, right? It goes from X to 1. So it goes away when you're dealing with the du at the end. The du is now just going to be something simpler. We'll talk about how to choose it in just a moment. This next one. Now, looking at what we did before, it seems like the correct choice. Now, don't write this down, but it seems like the correct choice would be u equals x cubed, right? We did it before with u equals x. Why not try u equals x cubed? Well, then du would be 3x squared dx. And because this is u, dv would be natural log of x dx. But we run into a problem. What's the antiderivative of natural log of x? The derivative of natural log of x is 1 over x. But the antiderivative of natural log of x, we haven't gone over that. We don't know what that is. Right? Unless somebody knows it off the top of their head, there's a formula for it, which we're going to prove to ourselves, but regardless. So this is out the window. This does not work. We need something different. So we don't give up. We don't do that. Not with integration. We don't give up. We just try something different. If nothing works, we go crazy. We just throw a bunch of darts at the board and see if anything sticks. We tried x cubed with u. Let's try the other function that's involved. Let's make u equal to natural log of x. Then du is equal to 1 over x dx. And that means that dv is whatever's left. dv is equal to x cubed dx. So if you want to write it with the highlighting, I'll stop doing this in a moment. That's my dv. dv, excuse me. And this is my u. So the antiderivative of x cubed. So I wrote the blue integral symbols in the previous one. I'm going to skip doing that from now on. We're just going to do that in our heads. We're just going to say, what is the antiderivative of x cubed, which is 1/4 x to the 4th. So v is equal to 1/4 x to the 4th. So once again, integral of u dv is equal to, say it out loud with me, uv minus the integral of v du. Say it at least. I heard you guys in your head saying it. Excellent. I'm glad we were all saying it together. Excellent. So uv is 1/4 x to the 4th natural log of x. Yeah, it's uv, so technically speaking, it would be natural log of x times 1/4 x to the 4th. But we like to see our polynomials first in mathematics, so we're going to write it that way. Minus the integral of v du, so 1/4 x to the 4th times du, which is 1 over x dx. And isn't that nifty? One of the powers of x will cancel. So we've got the integral of 1/4 x cubed, which is a power rule. So it becomes 1/4 x to the 4th natural log of x minus 1/16 x to the 4th plus a constant c. Boom, done. And if you want to prove this to yourself, remember, one of the great things about integration and differentiation are that you can check your work. If you take the derivative of this, you will see that you get back x cubed natural log of x. It happens that the 1/16, this term cancels with one of the parts of the product of this. It's pretty cool. Any questions on that? So this is the first of a few tools that we're going to be getting with this integration techniques. We're going to get this rule, we're going to get trigonometric integrals, we're going to get trigonometric substitution, and we're going to get partial fraction decomposition. There are more than that, but those are the core ones that we study because they're very, very nifty and they're efficient. Okay, so what I'm imagining a lot of you guys are saying is like, well, cool, Phil, you showed us how to do it, but how do I do it? How do I pick U and DV? And there is another acronym that people go by. I think they flip I and L, and they don't write polynomials, they write something else. But the way I learned it, and it's a great little term is LIPET. LIPET, LIPET. But above everything else, above everything that you want to do, the most important thing is to experiment. Be like my super straight edge, my mom, my friend's super straight edge mother. He went to Europe, and she pulled him aside as he was about to go for a Europe trip for high school. And she said, "Make mistakes." It was super weird to hear her say. Super weird. So make mistakes. It's okay. It's okay. If it doesn't work out the first time, maybe it'll work out the second time, or the third time, or the fifth time, or the 20th time. You just have to keep trying. So, but the intuition is what I want to talk about. We're going to be different. When we start these out, we always choose a U and a DV. So what we want to do is we know that we're going to have to differentiate U. So we want it to get simpler. So that's why we chose U equal to natural log of X in the previous one, because we went from a logarithmic function, which is arguably a difficult function to work with, to a power of X. It's X to the -1. Nicer to work with. And next, because we're going to be trying to integrate dv to get v, we want dv to be something that is easy enough to integrate and that hopefully won't get too overly complicated once the integration is done. So as such, we have this choice of system. Whenever you look at an integral, if you're going to try integration by parts, first look for logarithms. That's what L stands for. Is logarithms. So in this case, here, we look at this integral and we say, okay, there's a logarithm in it. That's our first choice. We're going to make u equal to natural log of y. So what should dv be then? It's everything else. So it would be a 1 over y dy. Now, we're not going to finish these ones. These are for you to practice. These are good practice problems. This one's kind of nasty, though, actually. But regardless. So logarithms come first in order. If you have a logarithm, make that your choice of u. Next is to choose inverse trig. Inverse trig. Now, the other textbooks will have their own little mnemonic device, or if you look online, they'll have their other one, and it'll start with I instead. It'll do IL, and it's because logarithms and inverse trig, they're about equal on terms of how good they are. I find that logarithms are nicer, and I prefer to choose logarithms first, but inverse trig, if you have a logarithm and inverse trig in the same problem, it doesn't really matter which one you choose. One of them will be good. So with this one, we'd make u equal to tangent inverse of 1 over x. Not tangent inverse of x because there is no tangent inverse of x here. We have to make u equal to the entire inverse trig function. So then what should dv be? dx. That is okay. It is okay. And that's what we're saying down below. I know I'm like, if you looked ahead, you could see that. but it's okay to make dv equal to dx. Next is polynomials. So if you see polynomials involved, and this can be monomials, right? T is a monomial. T is a monomial, so it's okay to use that. We'll make u equal to t and dv equal to everything else. That would be e to the negative 3t dt. And going back to our intuition, everyone's written that down. We should take our break after we get LiPed done. Going back to our intuition, this is a nice enough function to integrate because this will be negative 1/3 e to the negative 3t by that little nifty trick we saw in this 1.0 section with those ax plus b's. So that is a nifty choice. That is a useful choice for dv because this is a nicely integrable function. It's not like e to the negative 3t squared plus 7t divided by t. That would be pretty awful. Anyways, next thing, and then E and T, they are also kind of a situation where both kind of work out, but I find that exponentials are far better first. So exponentials. So with this one, e to the negative theta cosine 2 theta will make u equal to e to the negative theta and dv equal to whatever's left. So that's cosine of 2 theta d theta. Because much like the other one, cosine 2 theta is pretty nice to integrate. Nearly 1/2 sine of 2 theta. And last but not least, trig. So with this one, you can try u equal to sine squared, or you can try u equal to sine of x. I would recommend u equal to sine of x. And the reason I'm doing this one, I chose this one specifically to say sometimes you can split it up into two pieces. That sine squared, you can separate that into a sine of x times a sine of x. So if u is sine of x, then dv is equal to sine of x dx. One thing of note is that this integral, this last one, is a pain in the patootie to do if you're going to do integration by parts. There's a faster way, which we will learn in 1.2. So don't really worry about this one too much, but all of these 4 other ones, good practice problems for integration by parts. So let's go ahead and take our first break, or not our first break, our only break. Sorry. Last semester, I taught a Math 126E that was 3 hours twice a day. So we had to take 2 hours. We had to take 2 breaks. So I was like, here's our first break, second break, and I'm traumatized by it. So, anyways, we'll take a break. Let's come back at 11:12. 11:12. Let's make it fun. All right, people watching the recording, go do some squats or something. I don't know. All right. So I realized after the fact, because it's just for first day jitters. I said that I was going to show a picture. Like I made the joke that I was going to show a picture of my son first. I never actually showed a picture of my son. So it's not that I don't love him. I just forgot. Here is him building the Mario. Like he loves Legos very, very much. We worked on the Mario block Lego. It's like 3,000 pieces. He did the whole thing himself. Not the like I gave him the pieces, but he was able to figure it all out. So he's a big fan of Legos. It's like that's his thing right now. We're building the Hogwarts the burrow right now as a family. Because if you don't know, Lego has a build together app, and it's really awesome. You should like if you ever want to play Legos again for whatever reason, you can have fun with them at the same time because it's super cool. I wish we had time to show it. I mean, maybe during a break again. Remind me of the Lego thing. And then this is him right here. I got a bunch of Eevee Mega Blocks because they were on discount because now Pokemon rights are for Lego instead, but this and look at that cheese. That smile. Okay. Anyways, that's my son. This is my other son. I'm kidding, son. Kidding. Okay. Anyways, back to the point. Back to the fun stuff. Back to the fun. Okay. So if we remember from the previous page, we had a problem with dv equaling natural log of x dx because we didn't know what it was. Now we will do it. Based on LIPET, the best choice for you would be a logarithm. And we have a logarithm. So we will make u equal to natural log of x. That means that du is equal to 1 over x dx. And therefore, since natural log of x is the only thing inside the integrand, dv will just be dx. So then that means that v is equal to x. So integral of u dv is equal to uv minus v du. And as such, u is natural log of x, v is x, so it's going to be x natural log of x minus the integral of v, which is x, times the integral of times du, which is 1 over x dx. On an exam, on a quiz, you don't need to rewrite the uv minus integral of v du. You don't have to write it. I'm just writing it so that we keep practicing it. I really recommend when you start off, keep writing it down so you can, that's just free practice. So the x's cancel, and we just have the integral of 1, and the integral of 1 would be x. So the answer is x natural log of x minus x plus a constant c. Now we know what the integral of natural log of x is. X natural log of x minus x plus c. We weren't able to figure it out until this point, until we found out about integration by parts. That was a stumper. That was a difficult one for mathematicians. Now we have it, and it's pretty quick. Okay. Any questions? So LIPET, logs, then inverse trig, then polynomials, then exponentials, then trig, in that order. That's what you should choose for you. So this next one. What do you guys think? What should you be? And above all else, by the way, you should always try and do a u substitution if you can. But this one, if you the only really choice that you could use for a u substitution would be u equals natural log of x, but that's just going to make it look muddier. That's going to make it look worse. So no integral substitution here necessary. So we go to one of our tools that we know. Our only tool that we have right now is integration by parts. So we could either try making u equal to natural log of x and dv equal to natural log of x dx, since we do know what the integral of natural log of x is now, but I don't necessarily think that's going to help. So maybe we should make u equal to natural log of x quantity squared. I want you guys to fill in the rest. Find out your du, find out your dv, and then use that to find your v, and set this thing up. I will slowly fill in details. Chain rule is going to be your friend here. And for people watching recording, I'm gonna pause occasionally and then you should pause the video, see where you're at. Pause the video, and then you should try and pause it as well and try and figure out from here if you can. Here's the next step. Here's the next step, and then we'll get the answer. So record it. I have the answer here if you'd like to check your work. just as a nifty little pro tip, I didn't say this last semester, but I should have. One of the things that I really, really recommend during these time periods, if you are stumped on it, look at the first step and that's it. And then seriously, don't look at anything else. Try and figure out what to do next. Really, really, like that's how you should be taking notes in mathematics. It's the best way to do it is to constantly be saying what you think you should do. Because if you're right, it improves your confidence and it just helps you get better at it. If you're wrong, you'll learn from your mistake. So right now, if you've already finished, you should ask yourself what you think you should be and DV should be with this second one. And then see if you're going to be right. So u will be equal to natural log of x quantity squared. The derivative of that by the chain rule, the outer function is the second power. So it goes 2 natural log of x to the first power times the derivative of natural log of x, which is 1 over x dx. So that's why, I mean, you could write it as 2 ln x times 1 over x if you wanted to, but I am fine with, this is going to make it easier to work with. And since there's nothing left inside of our original integrand to make dv, there's just that dv is equal to dx, which means that v is equal to x. So integral of u dv is equal to uv minus v du. So it's going to be x natural log of x quantity squared minus the integral of v, x, du. So 2x, 2 natural log of x over x. The x's cancel, and 2 is just a constant. And we learned what the integral of natural log of x is on the previous page. The antiderivative of natural log of x is x ln x minus x. So you can distribute the 2 if you really want to. It's fine to do so. There's nothing wrong with it. Or you can leave it as is. Because my rule for this class about simplification is you only need to simplify if you're going to use it for something. We're not using this antiderivative for anything, so we don't need to distribute the 2. Cool? Any questions? All right. Next one. Since this is a definite, we'll do this one together. What do you guys think you should be? Lipet. Logarithms, then inverse trig. Arcsine y, sine inverse y, however you want to say it. So u will equal sine inverse of y. So du will equal, we'll have to know our inverse trig derivatives. Do we remember them? That's correct. 1 over the square root of 1 minus y squared, dy, and dv, there's nothing left. So it'll be dx, or dy in this case. So v will equal y. And so this is a definite integral. So when I do the integration by parts, it's going to be uv evaluated from 0 to 1/2. It's going to be uv, so y sine inverse of y evaluated from 0 to 1/2 minus the integral from 0 to 1/2 of v du. So that'll be y over the square root of 1 minus y squared dy. And this is a great problem to show what we need to do in this class. Now, you might be great at this. I was never good at it. So what I always had to do is I knew like this is going to require an integral substitution. Just by looking at it, you got a y squared in the denominator. You take the derivative of that, like doing your differential, du equals 2y. That'll be able to cancel out that y. So this is going to be an integral substitution. Me, though, I can't handle doing that at the same time as doing everything else. So what I usually did is I would kind of underline this and call this 1 or call it A or B or C or just color code it and then do it separately. So that's what I'm going to do. I'm going to do it down here. The integral from 0 to 1/2 of y over the square root of 1 minus y squared dy. That way, I can take care of this and then bring it back in when I need it. But if you feel confident doing it all at once, be my guest. You're better than me. So correct choice for you would be u equals 1 minus y squared. That means that du is equal to negative 2y dy. So that means that dy is equal to negative 1 over 2y du. And if those are the bounds in terms of y, if we change them, plugging in 0 gets you 1. So I'm going to color code these ones. This one now becomes 1. And if I plug in 1/2, 1 minus 1/2 squared is 1 minus 1/4. That's 3/4. And yes, the bottom bound is larger. But remember, if you're going to change the bounds with respect to your new variable, bottom bound stays the bottom bound. Top bound stays the top bound. Like you don't flip them. You just keep them where they were. So we've got y, oh, wrong color. Y over the square root of u times negative 1 over 2y. The y's cancel. We've got the integral from 1 to 3/4 of negative 1/2 u to the 1/2, negative 1/2, excuse me. Because 1 over square root u is u to the negative 1/2. du. And du. Can't believe I forgot that. I almost never do. Okay, and so that will equal negative 1/2 u to the positive 1/2 over 1/2 evaluated from 1 to 3/4. Any questions? Because these are tricky situations because you kind of are having to stop your brain to do something else and then come back to it. So please ask questions if you're lost at all. The 1/2s cancel. That's good. So we have negative u to the 1/2 evaluated from 1 to 3/4. That's going to equal negative square root 3/4 plus 1. Because it'll be negative the square root of 3/4 minus negative square root of 1. And that'll be 1. And then the double negatives cancel out. So we end up with, we'll bring that up. We still didn't do the evaluated from 0 to 1/2 of y sine to the negative 1 of y. So we'll do that right now. That'll be 1/2 sine inverse of 1/2 minus 0 times sine inverse of 0. That will be 0. And then minus negative square root 3/4. That's a terrible square root. I should feel ashamed. Plus 1. All right. Now here, though, I want us to know our trig, our inverse trig. Sine inverse of 1/2 is, who knows it? Well, we know our trig. Or you can use your calculator, right? We have a calculator. Just make sure you're in radians. For this class, I don't think we're ever going to deal with degrees. We're always going to do radians. So you can use your calculator, or you can remember how it works. You're trying to figure out what angle of theta makes sine theta equal to 1/2. That y sine is the y, so it's got to be the baby triangle. So it's pi over 6. So at the end of the day, we have pi over 12 plus square root 3/4 minus 1. Any questions on that? Yes,
We don't need a plus c because it's a definite integral.
that is correct. Because it's a definite integral, we do not need a plus c. It should just give us a specific value. Any other questions? All right. We'll do another one. I'd like you guys to start working through this one. Choose your U, choose your DV. If you get stumped, look up at the board. I'll be choosing them in just a moment. People watching the recording, go ahead and pause it and try and figure it out. Here is the first step. The next step. And then, Here's the clue for the next step. Here's the next step, and then we'll be finishing off on the last one. So here's our answer. And I should have mentioned the reminder at first that the integral of e to the ax plus b dx is equal to 1 over a e to the ax plus b. That will be a very useful tool. And so I recommend writing that in your notes so that when you review your notes, when the final comes up to, or the quiz, you know what happened. So that's why we were able to do those integrations so quickly for the DVs. So this one required a second integration by parts. We broke it down, and this kind of shows you that disintegrating nature of what integration by parts is supposed to do. It goes from being an x squared now down to an x. And then it'll break down from an x now into a 1. So that's the nifty trick that integration by parts is able to do for us. It breaks things down. That is why we use it. Now, as a small little note about the algebra of all this stuff, if you didn't want to deal with this 1/2 right here, you could bring it out front and deal with it at the end. That is not wrong to do so. I just decided to keep it in there, but it's not wrong to separate it out. The one thing I will remind us of, though, is that by the integration by parts, this piece becomes 2 terms that is being subtracted, so we have to have parentheses here at first. Then you can distribute it, or you could keep it still in parentheses. You could change this to parentheses and keep this as a minus. That's okay. For people watching the recording, you could still keep parentheses here, but change this to a minus, and that would be okay. All right? Any questions? Okay. So we got a few more to do, and I don't think we're going to be able to finish all of them, but that's okay. I'll give the answers to the other ones for practice, but the integral of, I do want to take time to do this one. This one's a doozy, but it's a fun one. It's really cool. It's really cool. So it has an exponential and a trig function. Which one should we make u? The exponential, because of LIPET. So we will make u equal to, and then I wanted to color code this a little bit. So there we go. Yes. Don't write it below it. Write it above it. So what we're going to do is we're going to write u equals e to the x so that du is equal to e to the x dx. And dv will equal sine of x dx. So v is equal to negative cosine of x. So remember, the derivative, the integral of sine is negative cosine. So the u choice didn't make it disintegrate, but it did make it the same, which is okay. That can happen, especially if you use exponentials. So integral of u dv is equal to, say it in your head if like just kind of make sure you're trying to memorize it, uv minus v du. So uv negative e to the x cosine x minus v du, but it's a minus negative cosine, so I'm going to go ahead and switch it immediately to a plus. The integral of v du, so that'll be e to the x cosine of x dx. Okay? Not much better, right? But it looks pretty similar, doesn't it? We have e to the x sine x, now we have e to the x cosine x. So you could try and make u equal to sine of x and dv equal to e to the x and see if that gets you anywhere. It might. I haven't really tested it in a while, but it might get you somewhere. But as it stands right now, there's nothing really that we have other than integration by parts and U substitution. There's not really a good choice for a U substitution, so we just throw darts at a board and hope something sticks. Let's try a second integration by parts. Second IBP. And once again, we're still going to follow LIPET. And if it doesn't work out, then we'll go back to the drawing board and we'll cry a little bit and dry our eyes and then work on. So we're going to make u equal to e to the x again. So that du is equal to e to the x dx. dv is equal to cosine of x dx. So v is equal to, the antiderivative of cosine is positive sine. So with that in mind, now we don't need to worry about putting parentheses when we expand this with people watching the recording. We don't need to worry about the parentheses when we expand this with integration by parts because it's being added. It was only with subtraction because we need to distribute the subtraction. But here we can split it apart. And then what I want you to do is I want you to write this down again, ideally in a different color. So e to the x sine x dx is therefore equal to negative e to the x cosine x. And then we're going to split apart this into another integration by parts, uv minus v du. So e to the x sine x minus the integral of v du. So that's e to the x sine x dx. No, not that picture. How do I copy a picture? This is getting out of hand. Now there's two of them. There's an e to the x here, and it's being subtracted, and there's an e to the x sine x on the other side. I'm all with it with the prequel memes. I know the prequels. I was there when they were. I was there when they happened. So make sure you draw this in your notes. You got to actually add that. Don't actually. I mean, you could search it right now on like and find it. But anyways, what we're gonna do at this point is we're gonna add the integral of e to the x sine x dx to both sides. So it's the same integral. So now there's two of them. So it's 2 times the integral of e to the x sine x dx is equal to, and just to make it look nicer, I'm going to put the positive term first. So I'm going to make the negative term go second. But you can keep it as is if you really like. It's e to the x sine x minus e to the x cosine x. And we'll divide both sides by 2 to find out what the answer is. So this is a very weird case where we didn't actually finish an integration to find the answer. They kind of call these ones like cyclic integrals because it's cyclic. We had to, like you can keep trying again and again and again, and you'll keep seeing that things will cancel out, and you'll always just end up with this situation. And so we need to be clever about it. So the final answer is e to the x sine x minus e to the x cosine x, all divided by 2. But we found the integral, and integrals always need a constant because we're finding the general antiderivative. So that's a very weird one, isn't it? Isn't that cool? Isn't that fun? Being clever. So, we don't have enough time to go over all of them, but I do want, so over the weekend or tonight, I would really love if you guys could do these 3 problems tonight. For this one, the answer, and I'll have the solution when we come back on Tuesday. The answer is going to be pi over 4 minus natural log of the square root of 2. The other one, and this one is going to be like when you see it, you'll see that it's going to be very similar to part A. The answer will be theta sine of ln of theta minus theta cosine of ln of theta, all divided by 2 plus a constant c. And then the last one, I'm going to give you a hint on that one because that one's tricky. Well, actually, we'll talk a little bit about it and we'll get it set up for the last one, the last minute and a half or so. So hopefully you can see that part C is probably going to be solved similarly to part A. Yes.
Can I take a picture?
Oh, yes, absolutely. Please take a picture of it, guys. What's the name? What is it?
Okay.
Jose, that's right. Right. I will try to remember you guys' names as quick as possible. But those are the answers. Please, please, please. I beg of you to do these tonight. Get some practice. Let that UV minus VDU stick in your head. Try these two, and then maybe tomorrow try the last one. And so, is it okay if I move on? Does anybody still need to take a picture? So, this one, it says the area of you're going to find the area of this region. F of x equals e to the square root x. It's bounded by that curve, x equals 1, x equals 4, and the x-axis. So I've provided a picture because I don't expect you guys to know what e to the square root x looks like. It's this kind of slightly curved line. And so the area of the region is going to be the definite integral from 1 to 4 of e to the square root x. Now here's where things get interesting. You can try, so right now the only options at our disposal are u substitution and integration by parts. You can try and do a integration by parts here right from the start, but you will see, like, I think you should just try it for a second to see that it becomes nasty. It becomes very, very uncomfortable, because if you make u equal to the e to the square root x, your derivative becomes more complicated. So the hint is first make a u sub, then integration by parts. But I'm just going to say first make a u sub. That will do it. So that'll do it for this week. Next week we have our quiz coming up about 10 to 15 minutes on just 1.0 with a heavier emphasis on integration, specifically integral substitution. If you have any questions, please feel free to email me. If you want to check your answers on any of them, feel free to send me an email about it. Otherwise, you have a great rest of your day, a great weekend. Avoid social media. It's poison. Avoid doom scrolling. It's even more poisonous. And spend time with the people around you. Have fun. And go Seahawks, right? Go Hawks. Let's beat those Rams. I'm sorry, the Lambs, right? Because they suck. Anyways, have a good one.